In a previous video that I've done, I've shown you a calculation on how to do a start point and a start point for the time high and a start point for the time low, if you know the frequency. In that specific case, the frequency I've set let the frequency be 10 kilohertz. And if I can quickly go to my calculations, we said if it was 10 kilohertz, that works out that your total time, your period, must be 100 microseconds. And I've said in that specific example, I'm going to make use of 29%, which means that your on time must be 29 microseconds and your off time must be 71 microseconds. And we're also going to make use of timer 1, which is in the AVR. And I've also said that we're going to make use of a reference voltage of 5 volt at the end of the day, which we are reading, and that will determine what your duty cycle would be. So if your input voltage is 5 volt, the ADC output would be 1023, which indicates a duty cycle of 100%. And if the ADC output is 512, it's around about half of that, it should be 50%. So that's what we've said in the previous section. I've shown you how to do the scaling factor, which was this 0.09775. And yeah, then we basically said, okay, for a 10 kilohertz signal, your on time must be 29 microseconds and your off time should be 71 microseconds. So this is all old news for you. We've also calculated that the machine cycle time must be 62.5 nanoseconds as before. And basically what we did is we calculated that the start point should be, for a 10 kilohertz, it should be XFE30. Yes, and that should have been loaded into the TCNT1 register, which is a 16-bit register. I also showed you then how to calculate a general formula, and basically here is the general formula, which means the only unknown variable was the value that you receive from the ADC, or basically then the voltage that you receive on the input of the ADC. So this was the start point calculation of start point high, and I went further and I showed you that the general formula to calculate the start point low would be then this at the bottom here, which is what we see here. And we actually implemented that in a program, and I showed you that the operation was close to perfect. There was a slightly off, but that is normal in timers. So yes, we can see that that was the formula that was created. So what I've done then is, and again, what is missing here, not missing, what is the unknown variable is the ADC output, which is of course what you would adjust the input voltage to be. So I've only got this one variable, but then the next question arises, and that is, but can't we use a similar approach to basically change the frequency? In our case, I've said let's make use of a 10 kilohertz system, but what if you need to do it for 8 kilohertz or 11.5 kilohertz or whatever, or 12 kilohertz or 15 kilohertz or whatever frequency is required? So in that same manner, you'll see that a lot of these calculations are basically the same. So I've again started off by the assumption, I just took exactly the same assumption of 10 kilohertz. Again, took 10 kilohertz, and the same I've said scaling factor, that will not change, that exactly stays the same. And I assume that the ADC output is 297, just like before, which means your duty cycle is 29%, which means your time on must be 29 microseconds and the time off must be 71 microseconds. That is for a 10 kilohertz signal. So if we go to the formula now, this was exactly the same as previously, and this is where the general formula for the high time. I've calculated this, and we saw in this line here that it's 29% of 100 microseconds, but then we knew that the frequency would be 10 kilohertz. So and this is the one, this area here, this is where we want to say, but what if the frequency, I know now the frequency is 10 kilohertz, but what if the frequency must be 8 kilohertz? And then you'll see what I've done is at some point, because this is percentage here, this is why you will see the divide here by 100. That's why it's because it's percentage there. And this 100 microseconds is where I have changed this, because 100 microseconds is actually 1 divided by the frequency. Sorry. This, you will see what basically happened here is the 100 here and that 100 there cancelled out. It left me with 1 microseconds. That's where the 1 microsecond come from, divided by the frequency, which is also 1 over f, which is the period. And that then leaves me with this formula here, which is important to us, where the ADC, I know that the ADC output is received from an input voltage that I receive from the input of the ADC. And now I can also implement a second unknown variable, which is f, the frequency. So in my program, I can make space there where I can say, okay, this program can work for an 8 kilohertz or a 9 or a 10 or a 11 or 12 just by changing one variable. So this is the new formula then, if I would like to have 2 unknown values, but specifically what if the frequency is going to be changed. And in the same manner, if I can quickly go down here, in exactly the same manner, I have set, like before, we've set it's 71 microseconds, and that 71 microseconds, we know where that is coming from. If the on time is 29 microseconds, the off time would be 71. That is if the frequency is, of course, 10 kilohertz. And then what happened here is, and we knew this, we got from 71% of 100 microseconds, and that 100 microseconds was 1 divided by 10 kilohertz. So now I would basically change that to 1 over the frequency, and by doing a little bit of mathematical changes here, we can come up with a formula that looks like this one. And in this specific case, again, the ADC value is received from the output of the ADC, or then the input voltage that is changing to the ADC, but also F. You can now change F inside your program. You can actually, in the top of your program, as one of the values that you define, you can say what F should be. And I'm going to show you in the next video how that will be implemented. So now all of a sudden I've got a slightly different formula like this one here. If the frequency needs to be changed or can be changed, and that is for the start time for low, and this one is for the start time of high, which is this formula that we see here. And in my next video I'm going to show you how to implement that program, and you will also see then that it is working. That is it for now. See you in the next video.